So, hi, welcome to this talk. Compression Carcinized, dropping compatible compression in Rust. So this time, this needs a little bit of introduction. So I'm here sort of on behalf of two organizations, the Trifecta Tech Foundation and a company called Tweede Golf. They're very closely related, but distinct. And in particular, Tweede Golf does commercial work, and one of the projects that we've worked on that is relevant for this conference is TSP, the Trust Banding Protocol, which I don't know a lot about. That is what this talk is for. But I did work on sort of exposing the Rust internals of this project to Python and JavaScript users. So if you want to know anything about that, let me know later. So I'm mostly here, though, on behalf of the Trifecta Tech Foundation, which is a foundation that we started because it's easier to pronounce for English speakers than Tweede Golf. And also, it has a bunch of other advantages. So what we do is we are now the sort of long-term home of the open source projects that Tweede Golf originally started. And we work on a lot of foundational technological components that are just sort of at the bottom of everyone's tech stack. So in particular, we're working sort of on three pillars. The first one is the original one for time synchronization, where the flagship project is called NTPDRS. So this is an implementation of the network time protocol that I spoke about last year at GOSIM. And since then, this is actually now in production at Let's Encrypt, which does most of the HTTP certificates that we use. So every time you load an HTTPS page, then that code is some tiny cog in the machine of making that work, which is really cool. Still, though, we would like to see it be adopted in more places because we think it is just an improvement over the status quo. Next up, we have what we call privilege boundary, with the main project being sudo rs. So this is an implementation of superuser do in Rust, which we're now porting to FreeBSD, so porting it over to other operating systems and adding some extra, well, it's missing functionality for like system administrators. So for personal use, it's already very feature complete, but there's still some work left to do. And then the main topic of the day is data compression, with the flagship project being zlib-rs. So as you can sort of see from these names, we're mostly focused on Rust. We occasionally sort of go into other languages to do some things or read up on how they do things, but Rust is sort of the core of what we do. So with that, welcome to Compression Carcinized. So about that name comes from biology. It alliterates, which is why I picked it really, but it also has a deeper meaning, which is that this is a word for evolving a crab-like body plan. And as Rust users, with the crab being sort of our mascot, that is a very nice thought, that evolving into a crab is actually a very good survival strategy. It's occurred multiple times over the course of evolution. And I also just like the phrase, evolving a crab-like body plan. So what I'll be talking about today is mostly zlib-rs, but also some other projects that we will start in the future or hope to start in the future. So you might wonder, what is zlib? What is zlib-rs? So zlib-rs is a Rust implementation of a thing called zlib. And zlib is a library for data compression, in particular dealing with the very common gzip format. So it is able to create gzip files and able to decompress them again into their original content. And gzip, and therefore zlib, are very widespread, especially on the internet. So if you download a file like a binary here, this is the Rust language server, it's very common to see the gz file extension for gzip, because gzip is a pretty good compression format, and also everyone already has software on their device to decode this format. So there's absolutely better compression methods out there today, but the software just isn't as widespread. Even if you haven't downloaded Rust Analyzer today, it's likely that you've loaded a web page. And web pages are also very commonly sort of encoded using the gzip content encoding. So this is rustlang.org, but basically every site does this because it's really worth it. So hopefully this sort of drives home the point that zlib and therefore, or gzip and therefore zlib, are these really critical foundational components of a lot of software stacks, especially anything related to the internet. So what is zlib, though? Well, in practice, it is a C dynamic library that exposes a bunch of functions for doing this compression and decompression work. So here I've tracked it down on my machine. And if we look at what symbols it has, we can see it indeed has a couple that correspond to compressing and what they call uncompressing, weirdly. But in practice, this is the inverse step of decompressing the file or any other input. Then from a Rust perspective especially, these type signatures are kind of nasty, but this is just what they provide. So in particular, this stuff is unsafe. We need to be thinking about the C way of doing things. There's raw pointers in there, which we really dislike in Rust. And also this function returns an integer, but really it indicates success or failure. And so we have ideas for how we would design a better interface, but we don't get to do that because this is just the interface that Zealot provides and the interface that everyone in the world expects. So our goal is actually to use Rust to build sort of an imposter, a library that looks from the outside as if it was created by C, but secretly on the inside there is Rust with all its advantages. And the idea behind that is that we make upgrading to our implementation really easy. So even if you don't have especially sort of warm, fuzzy feelings towards Rust, this is a very easy upgrade process. We really make that barrier very low, and that means that hopefully we can get our, we think, better Rust code into more places. And that's ultimately what this is about. We don't want to be safe in theory, we want to be used and effective in practice everywhere in all tech stacks. But then, of course, if we implement this in Rust anyway, we may as well also expose it to Rust users directly. So if you are already using Rust, it makes a lot more sense to sort of import it directly in the way that Rust allows you to do. But the main aim is the much wider use case of everyone already using Zealot today that doesn't want to change their application just because some people that like Rust decided that that was a thing that was a good idea. So what we'll be covering today is, first of all, a crash course compression, sort of looking at what Zealot does. Why does it work? Why is it so widely used? Then I'll look at the current state of the implementation, and in particular, a bunch of benchmarks that we've done over the past, say, half a year. And finally, I'll look at sort of the future of this project and the future that we see for the other compression projects that we want to work on. So, what does Zealot do? Well, the core idea of this compression is, why use many byte when few do trick? Because many bytes are expensive. You need disk space. You need bandwidth. These are all expensive things, especially at scale. Furthermore, if you have a wire and you want to send bytes over it, then sending fewer bytes is faster than sending many bytes. And so especially if our compression and decompression steps are fast enough, then we can actually gain significantly on speed. We can get web pages to users faster, and it's well known that the sort of time to first render is really crucial for a bunch of metrics that we care about. So the idea here is that the total time of compressing, sending the now smaller number of bytes, and then decompressing is faster than sending the original number of bytes over that wire. And the fact that gzip is so widely used is sort of proof that this is actually the case, that the compression and decompression are fast enough to make that happen. Also, what we're talking about here is lossless compression. So this is compression where if we have a piece of data and we compress it and then we decompress it again, we get the exact input back out. This is bit for bit, byte for byte, the same thing. So what we don't get to do here is cheat in the way that formats like JPEG or MP3 do. For media, you can often forget detail, like merge adjacent colors, cut out pieces of sound that we just don't really hear as humans. We don't get to do that. We don't get to cheat like that. We need to actually faithfully reproduce the original input. So how do we do that? How do we store many bytes using few bytes? Well, the core idea of these algorithms is to look for a repeating structure in the input. So here we have the input string foo bar foo, and we can see that FOO is repeated in this input. And the idea is that we're going to represent this second occurrence of FOO by referring back to the first occurrence of FOO, by inserting what is called an offset length pair. So this offset length pair points back 6 characters to the F, and then goes on for a duration of 3 characters to point to the foo sort of subslice. Now, inserting these pairs is more worth it the longer the match is. So if we had 4 characters, that would be better than the current 3. And also for anything below 3, it just doesn't really make sense because representing this offset and this length takes more space than representing the individual character. Also, hopefully it's sort of straightforward to see how we go from this encoded representation, this offset length pair representation, back to the original. We just walk over it. Maybe we find literal characters, we copy them to the output. Maybe we find one of these pairs. We need to go back a little bit, copy from there. Reasonably straightforward. The tricky bit is finding the repetitions. So if you look at this sort of semi-arbitrary sequence of characters and try to find repeating sequences of at least 3, this is actually surprisingly difficult. And it's difficult for humans, but it's also difficult for computers, especially if we care about the longest possible matches, which give us the best compression. And in practice, especially for bigger and bigger inputs, this is just not possible to do sufficiently quickly in the general case. So we need to sort of restrict this problem so that it is actually feasible to do on a web page when you request it. So how do we do that? Well, the way that zlib thinks about your input is as sort of a tape of, in practice, bytes, in this talk, characters, because humans can think about characters more easily than bytes. And we're going to have a current cursor position, and we're going to see if we can insert an offset length pair at this current position. And over time, we, of course, move from left to right over this file, this input. Now, the first constraint that we're going to add is what is called the window. And the window is our search space. This is what an offset length pair can refer to. Anything outside of here that is within these gray squares is not in scope anymore. We can't reference that. So making this window smaller means that we have a smaller search space, but it also means that it is less likely that we find a good match for the current position. So this is sort of a trade-off between speed and how much compression we can achieve. And so in practice, a user can configure this because we can't really determine what the right trade-off is between these two things. Next, the sort of second setting that we have is the compression level, which is a measure for how hard we're going to try to find the best match within the window. So imagine that we're at the current position here, this F, and we search the window from left to right. Then the first thing we find is a match of length 3, FOO. And we have to decide whether we're going to call it a day and stop here, not waste more space searching, or not waste more time searching, or if we should sort of gamble and hope that we find a better match later on, but potentially waste time. And again, here, it's not really, like, we can't objectively say this is the right trade-off, so a user can configure this. At a low compression level, so like 1, for instance, you would stop finding the first decent match. At high compression levels, you would continue to search and hopefully find something better, but potentially waste time. So that takes longer. Now, this still wouldn't work because we would spend too much time per character of the input. So it would still be way too slow if you do it in the way that I sort of described. So there's one final trick, which means that we can share work that we've done before, or sort of remember it. The idea is that we map subsequences of the input to the indices where the sequence occurs. So we keep track of the fact that FOO occurs at index 0, and OOB occurs at index 1, etc. And then when we find another 3-character sequence that is already in this mapping, all we need to do to find a match is look at the indices for that sequence. So here, only the index 0 is of interest. Any of the other indices are guaranteed to not match. So we'll only look at sort of a vastly reduced subset of the total window for every new character of input. And this is what makes zlib work. It's what makes it work for the web use case, right? So hopefully the intuition is sort of clear now that because the kind of data that we send on the web has a lot of repetition, it has text, it has like CSS classes, it has keywords in JavaScript, even at low compression levels, we find a lot of repetition very quickly, and we can reduce the total number of bytes very effectively. One final detail that makes this work even better in the sort of web case is that these are streaming algorithms. So that means that if you load a web page, you don't just like wait for all the input to come in and then decompress it, but instead you start decompression as soon as the first byte comes in. All right, so that's the theory. How are we actually doing in practice? So the two sort of points of our strategy of world domination are, one, compatibility, meaning we don't want to be different from anyone else, and two, we need to come up with reasons for people to actually switch to our implementation. So we really want to be compatible, meaning that we expose exactly the same functions with the same type signatures, etc. So we want it, in some sense, be indistinguishable from existing implementations. But in order to get people to switch, we also need to be different in some way. And if we can't do it, if we can't compete on the API, we need to instead compete on, well, something else. What we decide to compete on is performance, because gain performance is sort of like servers can do more work. Phones go through their battery less quickly. So in practice, performance is really important to us. So let's have a little look at the competition here. Who are we trying to beat? Generally, when we talk about zlib in practice, we're talking about zlib Adler, or what I'll call zlib OG. This is an implementation from 1995. It's older than I am. And its main sort of purpose in life at this point is to just not break anything. It's to keep systems that rely on it working into the future. So it still supports quite legacy systems. So these are like 16-bit systems that are like very legacy at this point. And also it doesn't use modern hardware capabilities particularly well. So these modern CPUs have custom SIMD instructions and wider registers, but these aren't used explicitly by this implementation, and hence it really doesn't take good advantage of the hardware. Because taking advantage of the hardware capabilities is kind of important, especially if your servers do a lot of compression. Several forks were made, and the most prominent and open source of these is called zlibng. And its goal is good performance on modern hardware. So what it removes is a bunch of legacy support, so 16-bit support is out, a bunch of other stuff is cleaned up, but it remains fully API compatible. So it is a drop-in compatible replacement for the original zlib. And then also, it starts speeding up the various bottlenecks in the algorithm using these modern SIMD instructions that are able to just sort of like work through a lot more input at a time. And this turns out to be incredibly effective for the kind of algorithm that zlib is. So like 2x performance boosts for workloads like this. Then in the Rust space, we had one implementation until recently, which is mini-z oxide, which is a really nice project, but it's sort of a safe, which is nice, but slow, which is not so nice, Rust implementation of a subset of zlib. So it really doesn't cover the full API. It's not a replacement in that way. And also, like zlib OG, it doesn't use these SIMD instructions effectively, so it is relatively slow on modern hardware. And so zlib sort of fills the remaining quadrant of this matrix. It is still, it highly values the safety that Rust can provide, but also we don't want to compromise on performance because that is how we get our code to the places where it actually matters, where it actually runs. Like zlibng, we use SIMD to speed up the algorithm, and we use a bunch of other tricks as well to just make it faster. And we do actually, well, we aim to implement the full zlib API. We believe that we cover like 99% of use cases today, but there are a couple of missing functions that we haven't prioritized so far. So how are we doing with that? Well, these results are encouraging. So we're looking at compression speed here as a factor of speed up versus the original zlib. And we can see that the original zlib in blue here really performs quite poorly in that most of the other implementations are much faster than it. We see that mini-z oxide isn't really that much faster for the higher compression levels, which do more work. And this is just because it doesn't use explicit SIMD instructions. And we see this big gap of almost a like 2x improvement between the implementations that do and those that don't use SIMD. I'll say that this graph is accurate, but it's not telling the full story. It shows that zlib RS is faster, and this is true, but it is dependent on how much input we feed at a time. Because this is a streaming algorithm, it depends whether you give it like 32 bytes at a time, or a kilobyte at a time, or a megabyte at a time. And that sort of shifts the balance in favor of zlib-rs or zlib-ng, sort of depending on how much input you give it. So we see sort of a similar picture for decompression, which, if you think about it, occurs a lot more often, because this occurs on all of our phones and all of our laptops all the time. And again, there is a sort of a clear difference between the implementations that do and those that don't use SIMD. And this time, sort of the balance tips in favor of zlib-ng, which is slightly faster for the particular input and sort of how we break it up into chunks for this benchmark. But if we zoom in on that a little bit more and look at feeding at different amounts of input. So on the bottom, we have chunks that are powers of 2. So we feed it 2 to the power 5 bytes or 2 to the power 10 bytes. Then you see that sort of a kilobyte and more, the Rust version is actually more performant by about 5%. And we'll go into exactly what explains that 5% in a bit. So this is on x86, where we, in practice, beat zlib-ng in most cases. So we want to figure out what's going on over on the left there. Because these implementations are now hardware specific or target specific, we need to redo the work on all of these targets. So we tried this on one of Huawei's servers. So thanks to Jonathan Spender for giving us access to one of these compounding servers. And in this case, we see a very similar trend. But in this case, we're only 2% faster. And there is a story. It looks like it's worse, but it has a good explanation. And finally, this company called Devolutions asked us to look into WebAssembly optimizations. So as far as we know, we're on the fastest WebAssembly implementation of zlib, beating zlib-ng by about 20%, because we now use the SIMD GOSIM instructions, and zlib-ng doesn't yet do that. So we blow them out of the water on this benchmark. I suspect that they'll eventually catch up, but the data for the other targets gives me confidence that we'll probably still beat it. So why do we beat the C code? How is that even possible? Isn't it supposed to be the case that you can do anything in C but faster because you have more control? And this is probably true, but it really depends on how much pain you want to go through as a C programmer. So in our case, what we do is we have very detailed benchmarks of the metrics that we care about, and we try to now really be sort of careful about the streaming use case as well. Next, we do a lot of staring at assembly. This is how hardcore we need to be to actually optimize this kind of code. And when something doesn't look right in the assembly, what we now have had to do is actually go change some stuff in the compiler to give us better code generation. So in particular, this relates to how state machines get compiled. So Björn 3, a well-known Rust developer, recently joined Trifecta and Tweede Golf. And he said, like, well, let's just try and fix it. And so we did. And this is the difference between the 5% on x86 and the 2% on ARM. This is like on x86, we applied these extra optimizations. On ARM, we didn't. And so it turns out that pretty minor changes in how code gets generated have a big impact even on the tight inner loops of our algorithm. Code that is supposed to already be very efficient, or at least, well, yeah. Like, it's been written to be efficient. And we're looking into like how to upstream that actually into Rust properly, because right now it's a bunch of hacks that works for our particular project. All right, so how do we evolve more crab-like body plans? How do we keep sort of pushing Rust into the future? Well, a big problem here is funding for this kind of work. We think it's very important. I hope that I've sort of shown that we're very serious about actually outcompeting C and being a stable foundation for the next several decades. We've already seen considerable interest from like projects that want to adopt this Rust version because it's an interesting proposition to them. But we need funding in order to sort of continue development and be able to like fix bugs as they come up. If you want to help with that, here's a link. that you can use to learn more about what is still missing, what we still want to do, what we need to do in order for this to be actually production ready. Of interest is that Mozilla is very interested in using this implementation in Firefox. So we already passed the test suite that they have, and we're now sort of working towards getting it into nightly and hopefully eventually into the production builds of the Firefox browser. And this is something I can talk about publicly, but there's many other parties that have shown sort of significant interest into actually using this in production, sort of like convincing us that the strategy of having these drop-in replacements is actually a good one. Then, as soon as I get back home, I'll start another project for bzip2. This is a less well-known compression algorithm, but it's still everywhere because it's in the zip file format. So it's somewhere in a lot of tech stacks sitting there. And so we also want to upgrade it. Here we got funding from Nelnet, from their Next Generation Internet fund, which we're very happy with. And they've been very good partners over the past couple of years with a bunch of our other projects as well. And this time what we want to do is try a tool called C2Rust. So this is a tool that is able to automatically translate C code into terribly looking but correct Rust code. And so we want to see if that is perhaps a better way for performing this kind of like rewrite work. Because what we've noticed with zlib itself, which we ported in a much more manual way, is that we get a lot of tiny logic errors. So the advantage is that you can sort of innovate architecture-wise, but the downside is that these logic errors do sort of hide in your code base, and you have to go track them down using fuzzing or bug reports or stuff like that. So hopefully C2Rust can sort of like smooth out that process a little bit. In any case, we'll gather some interesting data. Then what we want to do in the future is Z-standard. Z-standard is really the successor of zlib. It's an improved algorithm. It's faster. It gives better compression. And it's very likely that this is going to be the algorithm of the future. It's just now being integrated into a lot of projects. And wouldn't it be really nice if we actually started from a safe, solid foundation in a memory-safe language, instead of the C that is implemented by Meta, which is really the only implementation of it that exists. So, you know, maybe some other tech company should also get in on this, and we should build a good open source implementation sort of from the start, before it gets into everything. This is pending funding. And then also XC is an interesting candidate. XC is used for like having very good compression, which takes a lot longer. You can't really use it for loading web pages, but it's, for instance, used for distributing Rust releases, where saving the bandwidth is really worth it, and investing a little bit more CPU time once to compress it better is sort of a good deal. Again, pending funding. All right, so compression is very useful. Why use many bytes when few do trick? And compression is everywhere because it is extremely useful. In particular, it is everywhere on the web because it is unreasonably effective on web content. There is so much repetition in your JavaScript, in your CSS, that even spending like very little CPU time, we can really reduce the total payload that we have to send over the wire. You can try zlib-rs, especially if you're already using Rust. This is very easy, but we actually now also support building an actual C dynamic library. So you can actually try this out. I would say that it's not quite production ready yet, but it is very close, and we would really like your bug reports if you do run into anything. Also, let us know if it did work out of the box, because you know it sort of makes our day. In general, use more unglamorous Rust in production. There's a lot of like Rust projects that are really close to or really mature. So I'm thinking of Russell's, I'm thinking of NTPDRS. There are many others in this space, and sort of using them in production, even if you do it quietly, is really helpful for the sort of work that we do and sort of like furthering Rust in the world and having its nice properties actually have effect in the real world by upgrading all of these old, dusty software stacks. Finally, keep evolving more crap-like body plans. Thank you.